let's look at ions now. The movement of ions is different. Because why is ions, what the movement of ions rather has a different implication. Why? Because they are charged molecules. So if you take an ion, so we look at movement of water, we've looked at movement of lipid, right? Soluble molecules, those are neutral, they are uncharged, right? But now ions, a different mechanism, right, or principle behind their movements or implication behind their movement. Why is that? Because ions are charged molecules like sodium, potassium ions. It is those guys have charges, so they're gonna cause. We're gonna see a different implication, right, for their movement. So same thing here. So I have a lot. Look at the first box, the first experiment at the top. We have two compartments still, compartment A and compartment B, right? So what happens? You have a lot of ions on one side. We have a lot of ions. The blue molecules are the ions. They're on one side of they are in compartment A. So this will create what? It's going to create what? A concentration gradient, right? Yeah. So if you have molecules, a lot of molecules on one side, there's going to create a concentration gradient that wants to push or drive the molecules, right, from A towards B, right? That's why you have this big arrow pointing in that direction. Okay, good. So that's the concentration gradient trying to push the molecules to compartment B. Now, quick question. The barrier here, right? This barrier between compartment A and B, right? This is a lipid soluble, right? This is a lipid barrier, is the plasma membrane. Let's say, I have a question for you. Let's say we leave this experiment, right? This first experiment at the top. We leave it till tomorrow. Will you see any ions in compartment B when we come back? If we leave this till tomorrow, are we going to see any molecule, any of these ions in this compartment B when we come back tomorrow?
In a lipid soluble this thing, right?
So this is a lipid barrier, right? What is dividing the compartment is a lipid barrier. So
the rate and distance concentration. I'm not sure how to answer the question because okay, wait, concentration gradient inversely proportional to the rate. The distance is directly proportional. So what would be the distance between A to B?
but so far, right, like you understand what is created. So you have a lot of molecules on this compartment. You understand what this arrow is representing, right?
Yeah.
It's representing
Yeah.
what the concentration gradient, right?
Yeah.
Which direction does the
Oh wait,
gradient want to
the
travel?
arrow means concentration gradient.
So if you look at this experiment, if I ask you, where will these molecules go? Where are they? What's their tendency? Where would they want to go? These molecules that we have in this compartment, these ions in compartment A, where would they want to go?
Compartment B.
They want to move to B, right? This empty space, correct?
Yeah.
Why? Why?
Because so that they will free up space.
Right, because of that's what we call concentration gradients, right? So concentration gradient is like a force. You have a lot of molecules, right? You know what concentration means, right? When you have a lot of molecules on one side. So we have a lot of molecules in this compartment. All these molecules, they're going to be bombarding into each other, right? And that will create an energy or force, the concentration gradient, that will push, right, the molecule to compartment B. Does this make sense? Correct? Correct?
Yeah.
So we have the force, right, that will push them. We have the force. The question is, can they go through this barrier now between the compartment? Can they move? So we already have the force, fine, but can they move through the barrier separating the compartments?
Yeah.
The barrier is a lipid barrier, is a phospholipid, plasma membrane. Can a charged molecule, these are ions, right? Charged molecules, can they go through the barrier?
No.
No. So if I leave this experiment like this till tomorrow, will you see any molecule, any of this ion in compartment B?
No.
No, you won't. What does that tell you about? So compared to compared to what we saw, right, with the lipid soluble molecules, right? Lipid soluble molecules, they can go through the barrier. So once you have a gradient, what happens? They're going to move. They're going to move through the barrier because they are lipid soluble, correct? Yeah. But for ions are not going to move. They are not going to move, right? So in addition to creating a gradient, a force that will push the ions across the barrier must be permeable to the molecules for them to move. Does this make sense?
Yeah.
Right. So if I leave this to tomorrow, nothing will happen, right? But now let's say I decide to make, right? I cannot change that situation. I put a channel, right? So look at the second experiment now, right? The middle one. We now put a channel, right? We put a channel in the membrane. So this channel now, right? This channel is what? Is an ion channel. It's going to allow these ions, these molecules, these ions, and these ions are positively charged ions, right? It's going to allow them to go from compartment A to compartment B. So you can see that what? So we now have two things. We have a force, which is the concentration gradient, and we have what? The membrane now is permeable to the ions. There's a channel. So guess what? The molecules will start moving, right? The molecules are going to start moving through this channel and they're going to start moving. That force will start driving them, right, into compartment B. So you can see now we start having, right, the ions, right, in compartment B. Does this make sense? You get this?
Yeah.
All right. Now, if remember, right, these are not just molecules, right? They are charged molecules. These are positively charged molecules. If I start adding, right, I started removing a positively charged molecule from compartment A, so in the middle experiment still, and I start adding a positively charged molecule into compartment B. What do you think will happen to the charges? Compartment A will start becoming what? Less positive, right? It's going to become more negative because you are removing a positive charge. Compartment B will start becoming more positive, right? Because I'm adding a positive charge to it. Does this make sense?
Yeah.
Right. So now we are creating what? An ionic gradient now. We are creating a charge difference between the two compartments by moving an ionic molecule. So as you can see, so this little, right, this little small arrow now, this small arrow that start developing here in the opposite direction, right, of our concentration gradient arrow is now an ionic gradient because as I'm adding a positive charge, right, to this compartment B, this positive charge is building up, right, is going to start preventing more positive molecule from coming to this compartment B. Remember the principle of physics. Like charges will repel, right? Unlike
Yeah.
charges will attract. Does that make sense? So if compartment B becomes more and more positive, what do you think? It's going to start preventing positive charges from coming in, right? And that is why you have this small arrow, right, moving in the opposite direction. So, but as long as the big arrow, this concentration gradient arrow is bigger than the force by concentration gradient is bigger than the ionic gradient in the opposite direction, right? You're still going to be seeing movement of the molecule from A to B. Then this will continue. As this continues, this opposite arrow will start becoming bigger too, right? And then we're going to come to the third scenario. So you can see the last example at the bottom. Now we have both arrows are the same now. Why? Because now you have what? The concentration gradient in the forward direction is now equal to what? And opposite to the what? To the ionic gradient of force in the opposite direction, right? So when this happens, there will be no more movement between the two compartments. The molecules will stop moving. Because now, though we have a forward concentration gradient, the ionic gradient here in compartment B, this positive charge in compartment B, will impede the movement, right, of positive molecules into compartment B, right? So you will not see any movement anymore. And this is what we call what? Equilibrium now. We're going to say this molecule is at equilibrium because there will be no more net movement between the two compartments. Does this make sense? You get this? Awesome. Clear?
Yeah.
Clear? Right. So if I take an electrode, right? If I take an electrode and I measure the voltage in compartment A or this side of the membrane, it's going to be negative. If I take an electrode and I measure the voltage in compartment B, right, it's going to be a positive volt, right? Okay. So that's significant, right? All right. Let's apply this to the body, right? Let's see what happens in the body at rest. So let's take the body, right? So look at the top. We have ECF. So change comparison A and B, right, to the ECF and ICF, right? So here is the cell. We're in the cell here. This is the intracellular compartment on the right side, and the left side we have the extracellular compartment. Which positive ion is abundant in the cell? Which positive charge is abundant in the cell? It's potassium, right? Yeah. Potassium is the most abundant positive charge or electron, right, in the cell. Does that make sense? We are right.
Yeah.
That is a fact, right? So that's why we said that what the body is a what the cells are bags of potassium that are floating what in a sea of salts, correct? Because you have a lot of sodium chloride outside the cell, so a lot of sodium outside the cell, yeah, sodium chloride outside the cell, and then you have a lot of potassium in the cell. So these cells are going to be bags of potassium, and they're going to be floating in a sea of salts. Good. So in the ICF, right, you have potassium. So let me ask you, where will what do you think potassium wants to do? I have potassium in the ICF. What do you think it wants to do in terms of movement? Where does it want to move into?
Where does he want to move into?
Right, where? Which compartment will it want to go?
Compartment A.
It's going to want to go to the ECF, right? It wants to
Yeah.
leave the cell, correct? We have a lot of potassium within the cell in the ICF. Where will potassium wants to go? It wants to go into the ECF. Does that make sense?
Yeah.
Right. Why? Because of the concentration gradients, right?
Yeah.
Right. So will potassium move though? So you have your lipid barrier like this. That is,
No.
will potassium
No.
move?
No.
No, it's not going to move because the barrier is not permeable to potassium. Potassium is a charged molecule, right? So what must happen for potassium to move? In addition to having a concentration gradient, I must make the barrier, right, permeable, right, to potassium. Does that make sense? Yeah.
Yeah.
So what do we do in the second experiment now? We had a potassium channel to the membrane. We
Yeah.
insert a potassium channel. Good. So once you insert potassium channel, what happens? Potassium will start moving from the ICF. It's going to start moving to the ECF. What
Yeah.
will happen to the charge in the ECF, in the ICF? Sorry, what happens to the charge in the ICF? Will it become more positive or more negative as potassium
More.
start leaving?
More
It will become
negative.
more negative because you are removing what? A positive charge. Does this make sense? Yeah.
Yeah.
So the ICF, this side of the membrane, the part of the side of the membrane, plasma membrane within the cell, will start becoming more negative. What would happen to the side of the membrane outside the cell? It will start becoming what? More
More
positive. Does
positive.
this make sense? Because you are adding a positive charge. Thank you very much. So if I'm adding a positive charge to the ECF, that will now create what? An opposite ionic gradient. Can you see this small arrow now that I start developing, right?
Yeah.
Because like charges will repel. This positive charge now will start repelling the movement of potassium because it is a positive molecule. Good. So, but potassium will keep moving though. As long as the big arrow is bigger, right, than the small one, the force will keep pushing potassium out of the cell. Then this will continue until what you now get to the bottom. At the bottom now, you now see, right, the concentration gradient arrow is now equal and opposite to what? To the ionic gradient arrow in the opposite direction. So what happens? The force will stop. It's going to this gradient, the ionic gradient will stop. It's going to counteract and rule out the concentration gradient. So when this happens, will you see any further movement of potassium?
No.
No. So potassium stops moving. Right. So potassium stops moving. It's gonna stop moving. So when this happens, right? But we already created what? We already created that voltage. Though there's no more movement of potassium, but before that stops, you already have voltage difference, right? Right, or more called potential, membrane potential difference between between both sides, right, of the membrane. So such that the inner side of the membrane, the ICF side of the membrane, is going to become negative, while the ECF side will become what? Will become positive, right? And this is what we call your resting membrane potential. This is why in the body, right, normally at rest, a cell that is not disturbed, right, you are not stimulating that cell. That cell has a negative membrane potential. That is, if you measure the inside of the cell is what is going to be negative. It's about negative 90, right? Yeah. And why is that? Because at rest, Cells are permeable to potassium. The cell membrane is permeable to potassium. There's an open membrane, potassium membrane, right? There's an open potassium channel on the membrane at rest of every cell. So potassium is always leaving the cell at rest. It's always leaving, and that will create what? This negative membrane potential right within the cell. That's why at rest our RMP is about -80 or -90, right? It's negative because the membranes are permeable
Yeah.
to potassium at rest.
Nice.
Yes, right. Does this make sense?
Yeah, it does.
Good. And you can also say that what the potential, right? This membrane potential, right, is what we call the equilibrium potential of potassium, or what also called the nearest potential. Those are other terms you can see, right? They're talking about the same thing. So let's review the general principle we just established here. The principle is this: two things. For ions to move across membrane, the plasma membrane, we need two things. We need a concentration gradient, so that the ion can move down, right? Its concentration gradient. And then we need what? The membrane to be permeable, right, to that ion. And how do we achieve membrane permeability? Is by having ion channels. That's why channels are important. You have each ions have their own channels. Some of the channels are open, some of them are ligand gated, some of them are voltage gated. But the key is right. We're gonna keep the membrane, make the membrane permeable to a certain channel, to a certain ion. Whenever a membrane, right, is permeable to a what? To an ion, the movement of the ion, right, will drive the membrane potential towards its equilibrium potential, right? For instance, if the membrane potential for what? For sodium is positive, right? It is a positive, and if you work it out, it makes sense because sodium will behave like this, right? So where do you have sodium abundant? Where is sodium abundant? Is it ICF or ECF? Where do you have a lot of sodium? ICF or ECF?
Yeah.
Sodium is abundant where? Is it in the extracellular compartment or within the cell? Huh?
ECF.
Is abundant in the ECF, right? Good. It's abundant in the ECF. So let's look at this. If this is our ECF, compartment A here is the ECF, compartment B is the ICF, right? Intercellular space. So the concentration gradient of sodium, we want to push sodium, right, into the cell. Does this make sense? Right?
Yeah.
Into the cell. So, but it won't move, right, until what? There's an opened sodium channel, correct? On the membrane. When we have that channel on the membrane now, the membrane is permeable to sodium. Sodium will start moving from the ECF into the ICF. So what happens to the chat and is going to continue onto what? You now reach the equilibrium potential of sodium. When we read that equilibrium potential, when the concentration gradient and the ion gradient are equal and opposite, there'll be no more movement of sodium. But by the time that happens, what happens to the charge within the cell? The charge in the cell will become what? Positive. Does this make sense? Right. And we're going to say that what this cell is what? Is depolarized. Are you on the same page? So
Yeah.
because sodium has does what? Sodium has made the membrane potential more positive. Remember, at rest, our resting membrane potential is negative, right? Anything, anything that makes that membrane potential more positive, we call that depolarization. Anything that makes that membrane potential, right, that resting membrane potential more negative now. So instead of being -70, -90, you make it -100, negative 120. That's what we call hyperpolarization. Does this make sense? You get it? Now,
Yeah.
if you depolarize a cell, let's say you make a membrane positive, like sodium does here, and now we repolarize it, right? We turn it back. So I want to ask a question. How will I turn this back to a negative potential? I can close the sodium channel, right? Close it and prevent sodium from entering the cell, correct?
Yeah.
Or I can open what? A potassium channel. If I open potassium channel, potassium will start moving from the ICF right into the ECF, and it's going to start making the potential right more negative. Does this make sense? Right?
Yeah.
Right. And that's what we call what? Repolarization. That is, you're initially depolarized is positive. You want to convert it back to a negative charge, or you convert it, but that would be repolarization, right? So this is a huge principle because this is how neurons depolarize themselves, their membrane. This is how you create action potential right in neurons. It's just basically by moving ions, right? between compartments. This is how the muscles contract. This is how the muscles depolarize, right, and contract, is by moving ions, right? So this is a very, very easy principle. There's nothing to memorize. The only thing you need to ask is like, okay, if I'm depolarizing, right, I want to make the membrane more, the inside of the membrane, the ICF of the side, the intracellular side of the membrane, I want to make it more positive. What do I need? Either you move a positive charge into the cell, or you move a negative charge out of the cell, or you move a positive charge out of the cell. That will make the sorry. If I want, yeah, positive. I want to make it more positive rather. Yeah, you move a positive charge into the cell, like sodium into the cell. I move a negative charge out of the cell, or I move a what? I move a negative charge out of the cell. That will make the membrane positive, right? Depolarization. If I want to hyperpolarize or repolarize, make it negative, I move a positive charge out of the cell, or what? I move a negative charge into the cell, right? That will make it negative. Does this make sense? You get it? Awesome. Good.
Yeah.
Good. So this is a very, very huge principle, right? That